Okay, it's very cool to be with all of you here today. Stanford is my alma mater. I got my PhD here a few years ago, so it's really very emotional and cool to be back on campus. Even though I live for like 10 minutes from here, but I do not get the campus that often these days. Today I'm going to be talking about a very key issue in large language models, which is the issue of hallucination. So if I can get a show of hand, how many of you first heard about large language models, period? So that's about like 50% of the room. Hopefully the other folks heard about this as well, they're just still looking at their phones. And then how many of you heard about hallucination? Okay, it's about 60%, 70% of the room. And I meant hallucination within the context of large language models, not genetic hallucination. I will also talk about bias, which is another key thing that happen with these large language models, and how to mitigate for intellectual property risks as well, meaning the large language model produces something just verbatim the copy of something that might be copyrighted. So that's kind of a high level of the key topics I plan to cover today. But before I do that, I need to set the context for why it is important. So first, again, another show of hands, and I'll tend to do that a lot. That's how I wake up the audience every now and then. So how many of you, if you can raise your hand, if you have seen this chart before, raise your hand. So that's about 30% of the room. 30% of the room saw this chart before. So for the remaining 70%, down here you have the number of days. And up here, you have the number of people who have taken the eight up there is 100 million. So this is how fast different services across the world was able to reach 100 million users. So you can see Netflix, you can see Twitter, Facebook, Spotify, Instagram. ChatGPT is a delta function. It's literally just like this. Right? Nothing in history ever grew at that speed. So the question to you is why? Why do you think that happened? Why did it experience that very, very fast growth? And I think the answer goes back to the beginning of computers. When computers was born at the beginning, the only way that we could interact with them, I think many of you have not seen that phase, but I've seen it briefly, was called the punch cards. There were literally things called punch cards, and you had to punch holes in that for the different instructions that you want to tell the computer to do something for you. And then you had to feed the cards, and you find bugs in them, and you get them, and you punch it in until you get it to actually work. And then we figured out the keyboard. We came up with the concept of the keyboard, and there was a predefined set of commands that we had to remember. For those of you, again, that were tenured enough to have seen DOS. So DOS is the first command line environment for Windows, for PC computers. And it was a number of preset words that we had to remember, not the computer. We had to remember these words, and we had to remember every single option that goes with these words to be able to get something done. And then Windows 95 and the Mac happened around the late 1980s, early 1990s. And that is why the significant shift happened away from command line to visual environments where I have a mouse and I have a menu and I can go on the menu and find the command I want. That opened up consumption of software to a whole lot group of people, but also meant we had to rebuild all of our apps. We literally had to build every single app we have ever built to elevate it from the old way of the command line to this new way of visual environments. And then the iPhone and similar touchscreen devices happened around the mid-2000s. And that's now where we could use our fingers. We can pinch in, pinch out, swipe right, swipe left, all these amazing cool things. Again, opened up consumption to a whole new class of people, but we had to re-architect and redesign entirely all of our apps to work with this new modality of interaction to leverage. And I think now we're at Nirvana. Nirvana is, can we interact with software and computers in the same way that we just interact with each other? I want something from you, I just tell you what I want. You ask me maybe a couple of qualified questions, and then you understand what I mean. I don't have to click on your menu to get you to work with me. You just work with me. And finally, software is at that step now. And that explains the function that we have seen. People couldn't believe themselves. Like, wow, this thing actually understands what the heck I'm saying, what I'm asking for, and what I'm asking it to do. And not only that, it's responding back to me in the same way that I understand other humans. It's not giving me a cryptic message, it's a natural language message. So this is our belief at Vectara. We believe that over the next 5 years, every single application, in the same way that they were rewritten for touch screens and rewritten for mouse and window environments, they will be rewritten again to take advantage of this new modality of interaction, which is the ultimate modality of interaction, of just verbally expressing what we want, whether that be spoken or written. And that will lead to significant efficiency for everybody that's a knowledge worker. Anybody dealing with knowledge or dealing with software in general will be 10 times to 100 times more efficient in many different domains by leveraging these techniques. We also see an evolution from search engines, which is the old way that we interact with information. You ask the question and you get a bunch of results that you have to click on to find what you're looking for, and you have to read all of them until you eventually find the answer. Today, we have answer engines, again, just like with ChatGPT, when you ask it what is quantum mechanics, and it just gives you the answer for what is quantum mechanics. But if we nail the answer correctly, then we can move from answer engines to action engines, and that's where the software is taking action on our behalf. But to get to this type of action engines, we have to have answer engines that never hallucinate, right? Because imagine, for example, if you're using this software to interact with the school system at Stanford, the different classes you have to take, and you tell it, I would like to take that class, this class, I would like to drop this one, do here, and just verbally, you just tell it everything you want, and it says, done, I've done it for you. And then he found out it just dropped out of Stanford for you, right? Because it hallucinated your intent. So we have to have 0% hallucination, meaning the model making up stuff on our behalf, before we can move to action and systems, which we will. But I want to stress, it's very important to solve that problem of hallucination. This is the high-level diagram that describes what Vectara do. There is 2 views in this view. I'm not going to go over them in detail given our time today, but you can see the upper view there. What we present to the builders or developers of using our platform is a very simple API. It's almost like only 2 API calls. There is one API call where you're uploading the relevant data around your business or your application, and then another API call where you issue your prompts. And that's it. You don't have to worry about anything else. You don't have to worry about which encoder model would I be using, and I'll explain that in a second, which vector database to use, which re-ranking cross-attentional model to use, which summarizer model to use. We just figured out the best options for you for the task at hand. So that's the main value prop of Vectara is ease of use. We make it very simple for builders, developers to build amazing applications leveraging these new technologies while solving the problem of hallucination. So now I'm going to show it down to get you to understand this in a more concrete way. So now I'm going to switch to my demo window. Give me 1 second. This is a demo that we built where we indexed a lot of content from the Stanford Graduate School of Business. And now we can ask questions about the program and about different things. And you're still going to get the actual documents if you want to go and read them. But the key point here is that you got to get the answer. So you can see 2 things happening here. It's my Wi-Fi might not be working correctly. So this is taking longer than expected. Give me 1 second. Yeah, turn it. Wait, please. Dang it. It's working, it's just super slow, really slow, the Wi-Fi. Our system also is a bit slow right now. But you can see what happened here is 2 things, right? First, you got the underlying, we call them the facts. Or you can think about in the old way of thinking, it's just a list of results. It's a list of results that match what you're looking for. But this list of results is not being fetched with the whole way that we have been trained on, which is keyword matching. Can I match this keyword to this keyword? No, these results are being fetched based on semantic meaning. So it's almost, you can think of it, there is a neural network that is reading each one of these results and correlating it back to the question you're asking to find the facts that are most relevant to what you're trying to do, regardless of keyword, regardless of language even. I'll show you that in a second. And then at the end, you get back a holistic response that addresses the question you have in hand. and this is the answer. And you can see how the answer has these citations that link back. This is where this conclusion was made from, 3, 6, and 9. This is where this conclusion was made from, 5 and 10. So that gives you the extra confidence that these results are grounded in the truth, grounded in the facts, and not made up results. And also gives you the ability to, I want to read more about number 3, then you can actually go down the rabbit hole and read more about number 3. Here's the other beautiful thing. I can take this query and I can translate this to a different language. So here I'm going to translate it from English to Korean. Let's hope this is the proper Korean translation. I'm going to take that, I'm going to search with that instead now. So I'm searching in Korean. And again, the comprehension engine that retrieves the facts, it doesn't care what's the input language. It will find the most relevant facts that match the question that you have up there. Because again, it's almost like it's a multilingual person that can speak many, many languages, comprehend them very, very well, finding from the underlying documents the fact that match. And then when we respond back to you, feeble human, we respond back to you in the language that you understand, which is in this case is Korean. But this could be any language, right? It could be any language for the question. And even the underlying facts here, these facts could have been in Spanish, Chinese, German, French, it doesn't matter. The engine is cross-lingual. It can speak all of these languages at the same time. So with that quick demo, and there's a bunch of other demos here, we'll send you these slides that means you can try them out and play with that. So how do we solve hallucination? This is now the more technical part of the talk. There's 2 ways to get large language models to work with your own data, right? So ChatGPT has been trained on publicly available data. If I'm using it inside of Stanford my research, I might not know about it. If I'm using it at my company or my law firm or my engineering firm, it might actually should not know, because these are our proprietary confidential information. So how do we get it to work with our own data? There's 2 approaches for that. One is called grounded generation. That's the approach that we have at Vectara. And then the other approach is called LLM fine-tuning, large language models fine-tuning. So what is large language model fine-tuning? At a very, very high level, it's about taking an existing large language model and further training it with your own data, right? So the large language model has been trained on the publicly available data. Now I'm also going to give it my data and tell it to learn my data too, so it can talk about my data. So the large language model might have been trained on a bunch of public domain works or even copyrighted works, and you pay for the copyrighted works. That's part of what we do to train these models. And then now we're going to have a fine-tuning process, which is going to take your data and do custom training of that large language model so that you have a new derivative one now that knows your data, so your data now is part of its brain. And we can even tell it suppress these certain copyright. If we don't have you with some of these copyright works, we can suppress them. We can do what's called negative training to prevent the model from responding with a copyrighted work if you so wish to do so. And then when your question now comes in, your question will go to this fine-tuned model that knows about your data, and hence will give you a response that you might be familiar with and which will see as acceptable. So what are the problems with this approach? The first problem is this is a very expensive process. Training a large language model is very computationally expensive and also takes time, so slow. That's why ChatGPT is from 2021, the last knowledge it has, because it takes time to train it with newer knowledge. So that's the first problem with this technique. The second problem with this technique is it requires training on your data. And that has a number of issues now. The one key issue there is this model now knows about my data. It actually remembers and knows about my data. If this model is running with some other company, how can I trust that other company is not going to take my data, make its model more powerful with my data, and then come and compete with me later on? That's called model poisoning. So the model now has been poisoned with my own data or polluted with my own data, and now the model can be leveraged with other customers. So typically we'd only do this, by the way, if you control the model. If the model is running within your company, then you would trust to do something like that. It cannot cite sources. So I showed you the demo, the citation. When you do it this way, the model cannot really cite the sources for how it made its conclusion. That's something we're still working on to get large language models to do that. Second, you can think of a large language model very similar to how our brains work. When we go to Stanford, you're going to study tens, if not hundreds of books here at the university. Unless you have a photographic memory, which is very few of us have that photographic memory thing. I wish I had one. We don't store the book as is in our brain. You don't go in our brain and find the book content as is. We are storing a compressed representation of the key learnings and the key insights in that book, right? And when somebody asks us a question about the book, we recite it back to the best of our ability, but we're not going to recite it back verbatim exactly like it was. And in fact, we might use new words and we might remember things incorrectly because we're compressing so much knowledge. And that's where hallucination comes from. It's exactly the same thing. When a large language model is being trained on a massive amount of data, it's actually compressing it down significantly. We're talking about compression ratios of like 10,000 to 1 in terms of how much is compressing the knowledge. So as part of doing that, doing is now retrieving knowledge back. Every now and then, it will make up stuff. And that's what we refer to as hallucination. So when you do it with this technique, you're still going to suffer from that. And last but not least, if there was copyrighted or biased information in there, it will come out as is. There's no way for you to stop it. You have to depend on the provider of the large language model to solve these problems for you. So in a nutshell, these are the problems with large language model fine-tuning or large language model retraining. Number one, it will still hallucinate. Number two, it is slow and costly. Number three, it's hard to solve for copyright infringements and bias issues. Okay, so these are the drawbacks of this approach. So what's the advantage of fine-tuning? The advantage of fine-tuning, of training a large language model further with your data, is if your data goes beyond knowledge into world understanding or reasoning or planning, that now the model can actually capture these higher level concepts. You're not going to get this with the other approach I'm going to describe. So if your data is, for example, you have a historical data set of a lot of coding that you have been doing in a certain biomedical field that is not available in the web at large, then actually you want to fine-tune the model to learn this new technique. That makes sense? So if you have new techniques, doing fine-tuning is a good thing. If you have a style, hey, I would like you to answer this question in the style of Feynman and how Feynman speak, then this fine-tuning is good for that. Like these are some of the areas where fine-tuning is good. If you simply wanted to intelligently talk about your data and your content, no, you have all these problems I mentioned earlier. So the solution is grounded generation. You will also get it referred to as retrieval augmented generation. I'd refer to the acronym grounded generation because it stands for GG for short, and I'm a gamer, so that was my weakness there in terms of why I went with that term. So before we jump into how grounded generation works, grounded generation depends on a very important concept, which is a special neural network that can return meaning by understanding and not return meaning by matching keywords to keywords. It literally is finding content and finding information that match what you want to do by their comprehension value to what you're trying to do. These papers down here explain these techniques in a lot more detail. So how does grounded generation work? You still have the large language model. You start with a large language model that knows about English, Korean, German, Chinese, knows about our languages, knows about the domains, understands law, understands medicine, understands engineering, but then we don't train it with our data. We don't. What we do instead is this. We have another model, which is this information retrieval model, sitting ahead of it, digesting the input data as it comes in, not training on it, but simply digesting it and storing it in knowledge graph into a, again, photographic memory knowledge graph. This is retaining the underlying facts all as it is. It's not removing anything. It's not compressing anything. It's your data in its original data. And then when your question comes in, the question will go first to this comprehension network. And this comprehension neural network will return the most relevant facts that have to do with this question. And that's the only job it has to do. Find me the most relevant facts. And then once it finds these facts, then now we pass these facts into the large language model and we give it a very clear prompt that tells it, answer that question that you received following, but only use these facts. In fact, the longer prompt, I'm going to jump to it for a second and come back. This is kind of roughly what the longer prompt is saying. So if you go through the steps here, it's telling it, hey, pretend you're a search bot, you're going to answer this question, you're going to give a coherent response in the language of the question, You must only use information from the provided facts. Don't go hallucinate shit up, right? Only provide the answer as a function of these facts I'm giving to you, not a function of what compressed information you have in your model. Use the compressed information to understand the facts and reason about the facts, but don't make up stuff from that compressed information. Second, cite the facts are you using them in the response, and only cite the most relevant facts that answer the question. And last but not least, if the facts are of low relevance and not usable for the task, don't make stuff up, please. Just respond and say, I don't know. And that's how you significantly eliminate hallucination. It's almost zero, it's not 0% yet. We're working on that. And that's how we solve for bias. So now, even if the model has only internal bias, it will not lean on that. It will lean on what the facts are saying. Obviously, if your facts are biased, then it will continue to be biased. And then last but not least, if there was provided information inside the model, it will not eject itself out because the facts are preventing it from doing that. So in other words, we are sandboxing the large language model to only do the task at hand while minimizing the hallucinations coming from it. I already showed you folks a demo before, so I'm going to skip over that. And these are the main benefits of grounded generation. No need to retrain the model at all, so it's really fast, very cost efficient. There is no retention of your underlying data in a cleaned form, so no model pollution, so you're not worried about your data being used by somebody else. The facts are defined in the data that you're providing. The instruction in the prompts sandboxes us to these facts. We cite the proper sources, and then last but not least, new information coming into the system will show up in the response within a second, right? Versus with the retraining techniques, it takes days, if not years, before new information would show up. I'm going to skip over this slide, but these are some of the use cases that our platform is being used for. Again, we'll share the slides with you later. And then last but not least, if you would like to give this a try, scan that barcode up there. We give builders, innovators using our platform, we give them 50 megabytes of data that they can upload completely for free and 15,000 API calls per month completely for free. And only if you exceed that, then you have to pay $1.25 for every additional 5 megabytes. So that's it. That's my talk. Thank you very much. I don't know if I have time for one question or... Thank you.
Thank you so much for the awesome speech. Yeah. Okay. Yes.
What are we going to go on here?
Oh, okay. Awesome. Yeah. Yeah. I think we still have time for one question for the audience. So,
what's the hardest question? You need one hard question. See your hand over them.
Yeah. So go ahead. So you've already said that grounded generation and prompt engineering won't get you to 0% hallucination.
Yes.
What would?
Yeah. Very good question. The question is, okay, so even with grounded generation, you might not be able to get to 0%, but we need to get to 0%. So how are we going to solve that problem? It's a very hard problem. It's above my knowledge grades. I'll be honest with you. My co-founder, Amin, who also is an ex-Greek modeler like myself, that's his specialty. He's working on it very hard, but he's not the only one. OpenAI is working on this problem. Microsoft is working on this problem. Anthropic is working on this problem. There's some solutions around how we're the training itself of the models. And we're even looking at fact check of models. So having a model that sits at the output of the large language model that further confirms the facts that the model is reciting back, similar to how news reporters in any respectable news agency, before that article goes out, there's a fact checker that checks every thing in the article in case that reporter hallucinated some facts. So we think some of these techniques will work, but time will tell.